NaCl later. You get it? Saying bye to salt from groundwater. Our project is about the desalination of groundwater in Gabura Union, Bangladesh.
A village in Bangladesh with 42,000 residents faces a critical water crisis as their drinking water exceeds the salinity limits set by the World Health Organization due to rising sea levels exacerbated by climate change. Residents must walk 3 to 5 kilometers to purchase drinking water from plants that still fail to deliver affordable and clean drinking water. Our design constraints are energy usage, water quality, and affordability. The design can only use natural energy sources such as solar or tidal, since electricity is not consistently available in the village. The water must have a salinity level below that set by the World Health Organization, and the total unit for a family must cost less than 40 Canadian dollars. For the criteria or things we aim to have, the dimensions should be sufficiently lightweight and compact in order to allow people to lift and transport. The throughput should be about 16 liters per day, and the design should be able to withstand numerous cycles of water treatment without degrading.
Our approach was to design a system in which water evaporates, leaving behind the salt in the basin, therefore purifying the groundwater. To do that, we used materials that can be sourced locally in Bangladesh and took advantage of natural heat transfer in our system for condensation. Specifically, we use solar energy as our heat source. To observe our system's performance, we built a small-scale prototype, as seen in the pictures to the left, where we simulated the environmental conditions in Bangladesh and measured how much water evaporated.
Simulations were also done to determine the optimal size for the design. Through simulations, we were able to determine the dimensions of our system that would maximize water evaporation and condensation. Simulations were also performed to determine how closely experimental results aligned with predicted ones. This included determining the temperature of the glass, water, and aluminum throughout the day, as well as how much clean water is predicted to be collected. These simulations can be used further to determine the amount of clean water our design would produce for the community if we were to build a life-size model.
This project has several social and environmental benefits which can be measured through the UN SDGs and their indicators. Limited access to clean drinking water in this community becomes a gendered and socioeconomic issue as the burden of water collection falls to the women, and the people of lower socioeconomic status suffer as they are unable to afford to buy water. These units will be decentralized, empowering communities so they have control over their water. Only renewable energy is being used, solar energy, which also ties into social impacts as this community does not have access to electricity. The salt waste can be recycled and used in shrimp farming, which is a major source of income for these residents. This project, of course, aims to improve the health and well-being of residents as they can drink safe water.
Thank you for listening to our presentation.